Hello, Global Space School. It is my pleasure to introduce you to the next speaker. This is Mark Helmlinger. He and I were good friends in college. He has gone on to be a researcher at JPL, Jet Propulsion Laboratory in California. He is now working with instruments that have gone into space, some of which have been used for observation of Earth, observation of the moon, and some of the equipment that has been tested out for going to Jupiter and other planets. I am so excited for you to be able to hear his talk on sensors that have been used in space and also tested out right here on the ground. He does the, I think I'm getting too long here. Let's see if we can get started. Go ahead, Mark.
Hi, Glenn. I work in the imaging spectroscopy group. Let me share my screen here. Share. So I'm going to go through these slides fairly quickly. So if I say something you don't understand or you have any questions, please remember them and be sure to ask. I think Tuesday, Glenn, is when
That's right.
We'll have an opportunity to ask questions. This is a picture of JPL that I took myself with my cell phone camera out the window of an airplane while we were flying overhead, doing some remote sensing over JPL, testing out one of our instruments. And JPL is just north of Pasadena, California. And you can see it's in the Arroyo Seco, and it's right up against the foothills. So we have a lot of very nice paths up behind the lab to walk on. And it's a great place to work, and I recommend it if you can, in the future, if you want to take a look at working there. So I'm going to go to the next slide. There we go. So at JPL, what we do is we have the mandate, the NASA mandate for the robotic exploration of the solar system. We put America's first satellite in orbit, which was an answer to Sputnik. We were on the moon before the astronauts got there. There's a picture of an astronaut picking pieces off of one of our surveyors to bring back to Earth so we could look at how the moon, the environment on the moon affects our instruments. And then there's also some scientists with our rovers. Glenn, I don't see you. Is everything okay?
Yes, yes,
okay.
I was just getting out of the way, so you keep going.
Okay. So down there's a graphic about JPL's mission history, the places we've been, and at the very bottom, you really can't see it, but those are years. And so at a particular year, we went on a mission to either, well, every one of the planets in the solar system and asteroids and comets, and even Ceres and all kinds of other places. So notice there's a lot of green lines going to Earth. It's a very convenient planet to get to, and it's one we know a whole lot about. So when we learn about Earth, we actually learn about other planets. And when we learn about other planets, we learn about Earth. So one of our first remote sensing successes was taking a picture of the Earth with a slow scan black and white TV system in the days before there was digital image storage. You had to store it on Polaroid film and then slowly scan it back to Earth over regular analog television, black and white. And that's the picture on the bottom, which was taken 6 years before the astronauts took the upper picture, probably one of the most important photographs taken on color film of our lonely Earth against the cold blackness of space and the lifeless plains of the moon. It really was kind of an icon for the environmental movement because this is the only Earth we have, the only place we know of that supports life. So you all want to be asteroid miners, huh? Well, you're going to need one of these. A Star Trek sensor package, right? You want to, remote sensing is basically trying to figure out what's over there without actually going over there and touching it, right? So before you take all the trouble to fly to an asteroid, you want to do as much remote sensing on it as you can to make it an economic endeavor, right? So there's all kinds of different remote sensing instruments that you could put on a asteroid mining spaceship. They fall into two general categories, active and passive. Active remote sensing is like being in a dark room with a flashlight. You have to shine the light, it bounces off, it comes back at you. The active part is the flashlight. Passive is if the room is illuminated by sunlight, you're just looking around. You're not actively sending anything out, you're only receiving what's coming to you. So in the active category, we've got radar. LiDAR is lasers. That's what what the self-driving cars use to make a map of topography. We got ground penetrating radar, which is basically what it sounds like. Active EM, like a metal detector. TDEM is kind of like metal detecting, only it can actually sense water under the surface. You might be looking for a water ice. That and some solar power, and you've got rocket fuel, right? Hydrogen and oxygen. So you can also bring a nuclear source with you, radioactive material, or even fire X-rays stuff, and it'll make the materials in your asteroid emit stuff back at you, nuclear particles back at you. Or you can ablate it with lasers. We've actually got a laser beam on the Mars rover that's on Mars right now. It shoots out a laser and it causes a bright thermal plasma. And that plasma has what's called a spectral signature in it that can tell you what that rock was made of before you blew it up. We've got passive sensors as well, RGB, red, green, and blue imagery, which use reflected sunlight. We can do multispectral, which means more than just red, green, and blue colors. We can do several. We can look at things at different angles, like stereo vision, or even slant vision. We can do polarimetric, which is like polarized lenses. So that's all the information that's in sunlight. We're bouncing off of something, reflecting off of something. I do UV vis, NIR, ultraviolet, visible, and near infrared imaging spectroscopy, and that's what the rest of this talk is going to be about. That in one instrument, that's about the closest thing to a Star Trek sensor package you'll ever see, especially when it's coupled up with a LiDAR. It's a very powerful remote sensing package. There's also thermal infrared that you've seen the police and the military use, magnetometry. I'm helping with a mission to the Jupiter's moon Europa, and the mission's called Europa Clipper. It might launch on with a Falcon Heavy, in fact. And Jupiter has a very strong magnetic field. Well, we have magnetometers on it. I'm helping to test materials for those magnetometers, thermal and radiation. And as the magnetic field gets affected from Jupiter, gets affected by the moon, and they'll be able to tease it out from the orbits. The depth of the oceans beneath the ice crust on Europa, because we've pretty much figured out wherever there's water, there's probably life. So that's what we're looking at. We can also do nuclear radiation detection. There's cosmic rays bombarding stuff all the time, and natural materials give off their own characteristic nuclear signatures. And then you can do gravimetric displacement as well. The GRACE satellites measure gravity of the Earth, which is uneven, small amounts, but they're very sensitive, and they can make maps of the underground mass concentrations of the planet. They can even see depletion of groundwater due to a drought. So these are all various ways to do remote sensing, figuring out what's out there without actually going there and touching it. So warning, there's going to be some science ahead. Pay attention. So my instrument, the UVis imaging spectrometer, uses the middle part, so to speak, of the electromagnetic spectrum, right? And the electromagnetic spectrum covers a continuum, and you can only really sense a small part of it with your senses. Our instrument can sense a much larger part of it, and thereby gather more information than just looking at it with a color camera. So we use the solar radiation spectrum, and you can see under the word visible a little rainbow. That's the only part of the solar radiation spectrum you can see. But our instrument sees all of the curve. And the yellow part is the sunlight out in space, and the red part is after it gets through the atmosphere, what's left over. And then that's what bounces off the surface and goes back up through the atmosphere. So I'm going to stop sharing, I think,
Okay.
so that you can see what I'm doing. And then the camera is on me, I think. Right, Glenn?
Yes, it is.
Okay. So what I have here, I just turned off the light so you can't see it. is
We can see it fine. You got it.
all right. This is
Oh,
an
there you go.
integrating
Yeah.
sphere. I use a professional version of this in my work. It provides a uniform field of illumination for what's called flat fielding a camera or an imaging system, so that all your pixels, the gain of each pixel is adjusted so that you don't get snowy images, so to speak. And it's really good at homogenizing or mushing up. It's called an integrating sphere. Integration is a fancy mathematical word for mushing up. And so it mixes up the light in here and it comes out evenly. And what I have are 3 LEDs, light emitting diodes. And I have a red one in here, and I have a green one in here, and I have a blue one in here. And if I tip it forward, you might be able to see, sometimes you can see little
There you
dots
go.
inside. Yeah?
Yeah, there you go. We can see the green one.
Yeah, and there's a red one and there's a blue one. All right. So that's
Okay.
all that's in there, right? So when I turn all of them on, it looks white, doesn't it?
Yeah.
Right? Yeah, but there's no white light bulb in here. So where's the white light coming from? Let me really blow your mind. Does that look yellow?
Yes, it does.
All right. Well, there's no yellow light bulb in here, only red and green right now. So now let me turn the green one off, and I'm going to turn the blue one back on. That's what we call magenta.
Yeah.
And then I'm going to turn the red one off and turn the green one on. That's called cyan.
Yeah.
And so now I'm going to turn the blue one off and the red one on. So again, red and green is yellow. Now I'm going to turn the green, the red one up, and it should like get kind of orange, right?
Yeah.
And if I turn the blue one up, it'll get kind of chartreuse, maybe.
Okay.
I don't know. Our cameras. So
I'm not
this
real good with the term chartreuse, so I'm going to trust you on that one.
actually, it's a kind of a booze that monks make in France, and so yeah, you can look that up on the internet. It's this wonderful greenish color.
Yes, I saw
So
a greenish color.
all right. So anyway, your eyes can only really see red, green, and blue. If you took a magnifying glass to the computer screen you're looking at right now, you just see red, green, and blue dots. And it's the combinations of only those 3 colors that your brain uses to figure out what's going on. And your brain knows that yellow lies in between green and red in the rainbow. And so whenever you see even amounts of green and red light, your brain says, oh, that must be yellow, even though there's actually no yellow light there. So that's the difference between vision and seeing spectra. And we see spectra in a quantity called wavelength. So let me go back to sharing the screen. Share, right? So this is how scientists talk about color, even though only those wavelengths that lie within the visible range of wavelengths actually have a true color to them. So that's the distinction between the science. There we go. So when you're sensitive to more than just a few spectral bands, but a whole spectrum of light, there's a lot of information. When sunlight bounces off of materials, chemistry on the surface, it picks up information about what it bounced off of, what it reflected of. And we call that spectroscopy. Now, spectroscopy can be done directly on stars. So if you disperse white light from the sun into a spectrum, right, which is Newton did with his, can you see my cursor at all?
Yes, I can see it.
Okay, which is, he's holding up a prism and he's shining, he's making a rainbow. Fraunhofer made more sensitive instruments and actually by position was able to figure out that there's what's called absorption lines in materials. And then Hubble actually used it to figure out that the universe was expanding. So spectroscopy is a powerful analytic method for remote sensing. So we have what's called a push broom sensor that's airborne. And we've taken these in space and they rely like a platen scanner, right? You put your paper in a scanner and this bar goes bzzz across the paper. Well, the airplane goes bzzz across the countryside and we only see a little noodle, but that noodle builds up this imaging swath. And it's focused through a telescope, goes through our spectrometer onto our detector, and we get hundreds of parallel spectrometers out of this, which gives us an image cube. You see that word calibrated? That's my job. That's what I do. I calibrate it to make sure that it has physical units, right? Because just numbers is math, right? If I tell you 5, that's 5. But don't you kind of want to say 5 what? 5 miles? 5 oranges? You know, what are the units, right? Whenever you put units on a number, that's calibration. That's what I do. So the units I put on these numbers, the digital numbers that come out of the detector array are watts, basically, watts by wavelength. And that's what this reflectance number is related to. Anyway, we take this image cube and we take layers from it, we identify the minerals, and we make like a map. And this is what you're going to want to do around an asteroid. So we've got 2 different types of instruments, scanners and push brooms and whisk brooms. It's just to let you know there are different ways to do this kind of remote sensing. So again, our data comes through in an image cube, right? That image cube in the vertical, in the Z dimension, right, is all the different wavelengths. You see us 2 big black bands? Well, that's water vapor absorption lines in the atmosphere. Any planet with life on it is going to have those kinds of water absorption bands in it. So this is why we want to use spectroscopy to look at other planets, for example. But anyway, there's actually a black and white picture for every one of those layers. And for this representation of the data, we took the RGB layers, the red, green, and blue wavelengths, and represent them as a picture on top. This particular type of data was taken from an ER2, which is a modified U-2 spy plane. NASA's got 2 of them, and they have scientific instruments on them instead of spy instruments. And the pilot has to wear an oxygen suit, except for the people in the International Space Station. The pilot is the highest person on Earth when this airplane is flying at 20 kilometers. So here's, again, a mineral map for a place called Cuprite, Nevada. And over on the left is what we call an RGB image. It's kind of color exaggerated, but it's basically what you'd see if you were looking out the window of the airplane, so to speak. And then in the middle are 2 different types of mineral maps highlighting the distribution of the minerals. And for a geologist, the Earth is just looking at a surface. The Earth is like the exposed layers of geology. And so these are the exposed layers on the surface, and they can tell a geologist about the deeper layers. And so this is what you'd need to do prospecting for different minerals. So what they did is this is a slide saying that they were looking for calcite and dolomite, and they processed the data so that the little white dots were outcroppings of calcite and dolomite. And they said, well, let's pick a dot and go see what's actually there. And what do you know? They found calcite and dolomite at the little places that the imaging spectrometer said they would be. That's called a validation exercise. You want to make sure your technology works. We've also used this technology to map Superfund hazards, a place called Leadville, and the spectroscopy of vegetation, which can be mapped, is very interesting on a planet that has vegetation. There's all kinds of things you can tell about the species, plant health, and yeah, all kinds of good things about it. So here's Santa Barbara. We're looking at the species distribution, not only of Quercifus agrifolium, it's oak trees, basically, California oak trees, and where they're growing, and who's got a green lawn and who doesn't. See in the upper right image, grass is yellow, so that's where all the golf courses are and everything. So, and then there's these mountains just above north of Santa Barbara, and they have layers of geology, and there's certain plants that like one particular geology or soil versus another soil, and so you can see those speciation distributions change as you go up in altitude as well. So this is the kind of thing you can do with imaging spectroscopy. This is of a forest in the Shenandoah National Park, and all the different types of pine trees and deciduous trees and the distribution of that. And here we're looking at water vapor. So water vapor's got a very distinct spectral absorption feature. Even though it's completely invisible to the eye, this instrument can see all kinds of stuff that you can't normally see. We can look at corals in shallow water. We can look at the bottom. We can look at species distribution, how alive the coral is, whether it's dying because of climate change. There's all kinds of things.
Is this the Red Sea?
That was Kenoi Bay in Hawaii.
Ah, okay. Sorry. Go ahead.
Yeah, I didn't get to go on that one. Some people have all the fun. There's also something called a red tide, which is kind of a bad kind of plankton. It can kill fish and it can hurt you if you swim in it. And so we're able to find that. And we're even able to tell water from ice and snow. And yeah, the three phases of water, right? So water vapor we can see, and we can see ice and snow. And that's important for a place like Mount Rainier because when it warms up in the spring, you get these mud flows. Or volcanic activity can warm up the snow and give you a lahar, this big nasty mud flow. So these are ways of seeing things that you wouldn't normally be able to see, right? If you looked at it in RGB, it would just look like a mountain or a volcanic mountain covered in snow. And we can also quantify snow. Dark snow melts faster. And because of all the dust that mankind puts into the atmosphere, some snow packs are melting faster than they used to. And so this instrument's able to measure all that stuff. And then we're able, in Southern California, we have brush fires. And so not only can we predict what the dry biomass canopy is going to be and how it's going to burn. When it's actually burning and we fly over it, we can look at the temperature of the fire burning because we're looking into the infrared, and the fires are hot enough to give us enough energy in the infrared to quantify something called black body radiation. You might want to look at that on the internet. And so we're able to map out the severity and then look at the recovery later on of how well these places are recovering. We were called in after 9/11 to figure out where all the bad, nasty dust went from the collapsed buildings, and we were even able to find hot spots still burning deep in the basements in the buildings. We were the only plane flying at the time, in fact. This was quite a strange thing. We looked at the 2010 Gulf oil spill, not only the spill itself, trying to figure out where all the oil was going, but then we had data sets from before the oil spill, and we were able to get data sets just before the oil got there to the coastline, and then data sets of the damage that the oil did, and then the recovery of the coastline with time. We're also able to see the spectral signature of gases that are in between the surface and the sensor. So this is methane leaking out from an oil rig in the middle of the Gulf of Mexico. And this is natural gas leaking out from a tank near a natural gas well out in, oh gosh, where was this? I was there too, because I do something that's called ground truth, which is hard to do in space, which is why I want to do remote sensing. So we can do all these things, gases and surfaces. So my group built and sent this imaging spectrometer called NIMS to Jupiter. And we're thinking of and we are going to send one to Europa, because right now we just know that there's red goo in the cracks in the blue ice. And the red goo, we call those linea, right? Those cracks. So we want to get a spectral signature of those linea to see just if there's any life, evidence of life in there. So we sent VIMS to Saturn. We got spectra from that. And we sent CRISM to Mars, and that was able to find a material called gypsum on Mars, which you have to have a few million years of a shallow ocean to make gypsum on Earth. And so this was evidence of water on Mars existing for a significant period of time way back in the past. We've also sent one of our imaging spectrometers to the moon. And down in the lower left, that's olivine, which is a green mineral in volcanic rocks, and there's lots of it on Mars. Also pyroxenes and spinels and all kinds of other good stuff. But we also found water on the moon in the poles, because there's certain craters that never get any sunlight, and so they stay really, really cold, and that's called the cold trap. Any water molecule that goes wafting on by that either came out of the sun or is just minding its own business gets sucked into this and stays there, doesn't go back out. And so looking back at Earth, and this is how the aliens would see Earth from way off, or we would see an exoplanet from way off. we can see evidence of oxygen in our atmosphere, of vegetation, of water vapor in our atmosphere. If we saw these kinds of spectra coming from another planet, if we had a telescope that powerful, woohoo, we'd be building the warp drive, let me tell you. So spectra can tell you things about stuff that you can't see with your eye, right? So here we have some white powders. They all look pretty white. They're kind of hard to tell apart when they're all about ground up the same. And if I use a regular spectrometer, an imaging spectrometer is like having thousands of regular spectrometers, right? Because a regular spectrometer only sees one spectra at a time. I've measured the spectra of all those materials. Baking soda is the white line. It's fairly uninteresting. We call that an uninteresting spectrum. But we've got a sweetener, we've got salt, sugar, plaster, and flour, and they all have little bumps, dips, and wiggles. And those is what's called a spectral fingerprint or signature. And each one of those bumps and wiggles is due to a particular chemical bond between the carbon, the hydrogen, the oxygen, the nitrogen, whatever the material is made out of. Its chemistry interacts with photons and is responsible for these absorption signatures. So even dogs have chemistry going on. Isn't that something? These are the spectra of my dogs. Fairly, quote unquote, uninteresting spectra, but I was curious. So the one on the left is a mix between an Australian cattle dog and a border collie, and the one on the right is an Australian cattle dog, Queensland Blue Heeler. That's my favorite kinds. Smart dogs. So here I am at Perdido Beach, which is near Texas. I think it's in Texas.
I think you're right.
Perdido, yeah, and because this is the Gulf. And I forget what city, that might be Houston behind me, I don't know, or Galveston, I forget which. But these are the spectra that I measured while I was there of the white beach sand, right, which is dry, that's the white line. And then you can see the water absorption features where the spectra go crazy at 1400 and about 1800 nanometers. And that's because the signal to noise ratio, there's no light there basically. If you could only see at those wavelengths, the Earth would be dark all the time because of the water vapor in the atmosphere. So the readings kind of go crazy there because I'm dividing by 0 and other things. But notice there was a green bush, there was a parking lot with asphalt behind me. And so the asphalt is the orange line, and then you can see a characteristic curve of the vegetation. You see a bump at about 550 nanometers. Plants are green. 550 nanometers is, we perceive it as green light. Chlorophyll absorbs blue, which is at the 400 nanometer line at the bottom, and it absorbs red light at 650 and 700 nanometers. That's what makes plants go, is green and red light, which is why those grow bulbs are kind of magenta colored, because they've got green and red light in them. Or I'm blue and red light, sorry. No green, blue and red. And plants look green because they don't use green light as much as they do the blue and red. They reflect the green, and that's why they look green to us. And then that edge from 700 nanometers to 800 nanometers, that's called the red edge. Nothing else on Earth, no other chemical on Earth has that spectral feature. If we see anything like that on another planet, woohoo, we're in business. So of steroid. This is what's called a wrap over topography. The topography was determined by actually by a radar mission. It could be determined by a LiDAR as well. Space Shuttle Radar, SRTM, Shuttle Radar Topography Mission, is the base digital elevation map of Google Earth, and JPL built that instrument years and years ago. Anyway, it gives you kind of a three-dimensional view of the mineral distribution of this place called Goldfield. Well, in Goldfield, Nevada, some of these minerals are associated with gold. And so a geologist could look at this and figure out where gold is, where to dig, so to speak, right? Because that's the question, not only where to dig, but how much is really there? I mean, how much dirt do you got to move out of the way? And then how much is going to be there once you move all that dirt? That's called the economic viability of a deposit. And that's also what's important. Because you could be seeing just the last, you could either be seeing the tip of an iceberg or the last root of the tree that got wiped out a long time ago. So you never know until you quantify the entire volume of your mineable mineral. So this is the rocket science part. This is our instrument, our imaging spectrometer, sorry, in the clean room. And it's held in near space conditions, actually cleaner than space and about as cold as space. It's a thermos. We've got the shell off, and those are the guts inside that are normally exposed to a hard vacuum at cryogenic temperatures. Signals are conducted by little ribbon cables, and but that's what real space hardware looks like. And when we put our instruments in space, we don't put them in a can. We don't need to. It's already vacuum. It's already cold. And we design things to work in a vacuum and cold. But we put a can around it, right? So that we can have a little bit of outer space with us wherever we go. And you can see me down there on the left. And I'm actually calibrating this instrument by exposing it to known radiometric sources. And that blue thing is an integrating sphere. That's a professional one made by an outfit called LabSphere. So we then take those instruments that we've got in our little Bitto space cans and fly them around in airplanes, looking at the most important planet in the solar system. I have to remind my colleagues at JPL, yes, we live on the most important planet here. And we're flying, and this is called the Twin Otter, and it's an unpressurized aircraft. And this is what it looks like inside. Can you hear the audio of me talking? No, probably not. Anyway, we're at 16,000, and we're breathing oxygen. That's called the cannula. That's the readout. And we're actually trying to do remote sensing of methane in the atmosphere. There's the instrument in the back. And it's actually on a mount that compensates for the motion of the plane. And that's what it looks like outside. So every one of those little clear spots down there, let's look out the other window. Every one of those little clear spots is a natural gas well. And this is in the Four Corners area in New Mexico. And sometimes they get sloppy or something breaks and gas is released into the air. And that's what we were doing, was seeing how many wells were leaking, looking for rogue emissions. So this is what it looks like looking down along the side of the can out the bottom of the hole in the plane. Don't drop your cell phone. You'll never see it again. And it looks like it's moving, right? Well, actually, it's on a stabilizing mount. It's the airplane that's moving, and the instrument's sitting rock still because we're scanning the ground. And that's because the plane rolls just a little bit. So the mount compensates for the roll of the airplane. This is my my readout as an operator. On the left is called a waterfall display, and on the right is the actual focal plane array as imaged. And then you see that those little tiny squares on the left, that's actually our target in the middle of our acquisition line. So we got the target right in the middle. Each one of those little plots has a different plant in it. And the scientist who paid for us to take a scan of his little plot was able to make a library of spectra to apply to other data sets.
Excellent.
And that's what it looks like on the airplane. Now, when you look out the window sometimes, this is during what's called a transit from LA to central Colorado through Utah, through the steps near Zion and those kinds of places. This is Painter's Palette in Death Valley. Highly recommend the place if you ever get a chance to go. That's our landing wheel, you can see. This is the San Andreas Fault. These are salt ponds. They make salt in San Francisco, and as the water gets saltier, different species of plankton inhabit it, and the really salty ponds have the redder cyanobacteria in them.
That's real color? That's not false colors?
That's real RGB. I took that with my cell phone camera.
Wow.
Just a second. Honey, I'm in the middle of something. I'll call you back. Bye. So I didn't tell her we were doing this. It's kind of a recording. And I'm kind of quarantined because I'm flying right now, and I just got back from the field. I'm quarantined out here in the my off-road RV, which is where I'm sitting, so that we can be safe. And
Sounds like a good idea.
yeah, this is the Sierra Nevadas, and this U-shaped valley we're looking up. That's been shaped by a glacier, because back in the Ice Age there were glaciers that scraped these valleys out. These are the Sierra Nevadas as well, and this is Owens Valley, the beginning of the Basin and Range Province. And you can
That's
see
Long Valley Caldera, isn't it?
those are volcanic caldera, and they're there because there's a big crack in the earth where those mountains are rising up, and so the magma comes up that crack too. There's all kinds of hot springs. It's a magical place.
Yeah.
The Eastern Sierras. These are some of the exposed layers in the Escalante Steppes area. This is called an oxbow. This is the Green River, and some more area. That's the pilot's step that he has to step. See, it says step on it down there, and he steps onto that before he gets into the plane. So that was the Twin Otter. This is called a King Air, and this was our first King Air, tail number N42 Zulu, which is a great tail number. And this is what it's like to fly around in a King Air. It's a pressurized aircraft, so you don't have to wear oxygen masks. And right now we're in a turn. See how at the angle that the horizon is at there? Turns are nice because then you can just look straight out the window down to the ground. And we're over Wisconsin. It's really green. Now we're flattening out and you can see more of the horizon. So this is what our instrument looks like mounted in that plane. It flies a little smoother, and we have an improved inertial navigation system that allows us to compensate for the motion of the aircraft. So this instrument's taken me to India. Here we are at India, about ready to take off. And Bhubaneswar is a town in India, and we made the local newspaper there. Yes, this is what India looks like. A lot of people, a lot of stuff going on, and more cell towers than you can imagine. I have no idea why they have so many cell towers. And this is our airplane. They don't have private business airports, so we just pull right up next to the jumbo jets, and everybody on the jumbo jet gets off and looks at this little airplane and goes, what are they doing there? But there we are. And this is our new King Air. We rent these things from a company, and the company puts holes in the bottom so our instruments can look out, basically. And they rent them to all kinds of agencies and companies. This plane, you get the pilots, and they have a very deep credit card for all the gas. And our fuel is called Jet A1 because these are turbofan or turboprop engines. Anyway, this is, and you can see the Matterhorn's a little pointy mountain way at the end of the wing there.
Oh, yeah.
Yeah, that's the Matterhorn.
Good pointer.
Yeah. And then this is northern Greenland, and this is the last land before the pole. I'm within 4 degrees latitude of the North Pole, Greenland. And then here we are at Thule Air Base in Greenland, picking up some ice for our drinks later on. It's very cold. And then this is a mission I just recently flew over Ivanpah Playa, and where the California-Nevada state line is and Highway 15 crosses. Highway 15 is how you get from LA to Vegas, baby. And right here are some casinos right on the state line. It's your first and last opportunity, depending on which direction you're going, to gamble. Right there next to that play. And then these are solar power stations. This is photovoltaic, and these are solar thermal stations. A field of mirrors concentrates light on a central tower and boils water for a steam turbine. And this is what it looks like on the ground. This is called a playa. It's a big even surface, or homogeneous surface, we call it. We make measurements on the ground truth, so that when the plane flies over, we know what radiance the plane should see.
There he goes.
Thank you very much for your attention. If you have any questions, just let us know.
Mark, that was terrific. That's pretty darn exciting. Looks like you get to travel all over the world to be able to see and take instruments and then be able to do the calibrations for that. How many different countries have you seen by way of your job with JPL?
Well, I've been several places in Europe, Greenland. I've been to the Arctic. I've been to, did you know they have a subway in Barrow, Alaska? It's the furthest point.
Did not know that.
Been to Nome, where the end of the Iditarod is.
Uh-huh.
I've been to just about every state of the Union, certainly all four corners of continental United States. I've been to Africa,
What countries were
sub-Saharan
you in
Africa.
Africa?
Pardon me?
What countries were you in Africa?
Let's see. Well, I flew into South Africa, then drove to Botswana, and then drove west from Botswana into Namibia, and then up the coast to Etoshapan. And we were going to drive, which is in northern Namibia, and we were going to drive across the Caprivi Strip, which is between Botswana and Congo, over to the Okavango Delta, because there's a big dry lake bed over there called Suapan. I was doing reconnaissance. Well, first I did reconnaissance of one pan. Then I came back a few months later, did reconnaissance of another pan. Then I came back for 9 weeks and did the calibration experiment. And then I came back a year later to present results. And so I've been to, Namibia, Botswana. And then to present the results, that was in Zambia. And that was held in a resort on Lake Kariba. And just across the lake was Zimbabwe, and my wife took off for Zimbabwe while I was in the scientific meeting. So she's been to a country in Africa that I've never been to. So, of all the countries in Africa, I would recommend Botswana. It's a very beautiful place, and the people are wonderfully nice. Very peaceful too.
Excellent. So. All right. Thank you so much, Mark. We really appreciate your talk. And so I hope that everybody will tune in for asking him some questions about some of this remote sensing. I am certain that it is going to be valuable for your research on asteroids and how we might do some mining there. All right. Thanks again, Mark, and I'll talk to you soon.